Okay, yes.
Yes.
So the first talk was meant to be a bit more introductory of the institution. So here you will directly get a deep dive into some specific research topic, which I'm personally conducting jointly at Charité and Bifold. And basically, this is the topic of explainable AI in medical area to try to understand both data, so medical questions, but also machine learning models that are used in this context. So here, the title of this presentation is basically explainable AI for unsupervised learning. And why do we care about unsupervised learning? It is because of the nature of the data, which often is provided in raw format, raw data, without so much data curation. So if you think about the data, you can place it on some spectrum between raw data and curated data, where on one side you have the data as it is arriving, for example, from the acquisition device or the sensors. It might be noisy, it might be misaligned. There is no metadata or human annotations that come with it. And as you enrich this data with pre-processing, feature extraction, human annotation, then you get this curated data. So in practice, there are advantages to both types of data. For raw data, the advantage is that you can acquire very big data sets because nowadays sensors and acquisition device can massively digitize or create these large data sets. And it's also task unspecific. So generally the data that you are dealing with, raw data, is usable for a very broad sets of tasks. Whereas if you move from curated data, then you have like all this additional value which is added by the human annotators. But it is also fundamentally smaller because there is a time which is required, basically the time which or the cost of human involvement, and also task specific in the sense that you already know more or less what you want to solve as a task, or what kind of information you would like to extract in the data. And if you think of like general machine learning paradigms that we can place on these two types of data, on the left-hand side you have unsupervised learning, and on the right-hand side you have supervised learning. So now, based on this need for addressing unsupervised learning, because you have these large available data sets, and also being able to understand this unsupervised learning black box, I will go through two medical use cases. And the first one is more of a scientific nature, so trying to gain some scientific understanding out of data. And the second one will be in the context of foundation models. So I will start with the first one, where what was the focus of our investigation was to try to build or to infer a regulatory network from omics data. And the data we were dealing with is essentially protein concentration data in different subjects. And what we wanted to ask as a question is whether different protein concentrations are related, and that might, for example, suggest some regulatory mechanisms between those proteins. And what is also critical is that this study involves many different subjects, and what happens in one subject might differ from what happens in another subject. And so basically what we would not like to only obtain data set wide insight about whether there is a link between two specific features, but we would also like to get something which is organ specific or subject specific. And in that sense, if you think about classical correlation, which would be the most simple way to address this problem, this is not very suitable. Because if you want to ask a question about a very specific subject, very specific organ, then you might not have enough data to support the correlation. So the idea was to try to use the power of machine learning models, and especially machine learning made explainable, to answer this kind of questions. So one supervised approach we could use. One approach we could use for that is that of link prediction that you can find in supervised learning. But we didn't pursue this approach because this would require that we have actually ground truths about the interactions between the different features. And we might have them at a course level, but not on a subject-specific level. And this would be just too costly to acquire. And so we went the unsupervised route, where we had to basically define some unsupervised task, which is a good surrogate for the task we would like to solve, which is to infer this relation between different proteins. So the approach we went with is that of in-painting. So if you think about the case of images, for example, it would be, for example, the autoencoder, where you hide some part of the data and then you try to reconstruct what is missing in the image. Here we are not dealing with images, we are dealing with networks or with tabular data, so basically arrays of protein values. And so here we took basically a similar approach, which consists of hiding some of these protein values and try to reconstruct them from the other values. But this is just a surrogate task, and it's not so close to what we really are interested in, which is to infer this network. So basically to try to find if there are links between these proteins. And for that, it's not sufficient to just train the reconstruction model, which basically tell us from certain amount of proteins how accurately the other ones could be predicted. We also want to be able to trace back the connection from protein to protein, which basically support the reconstruction. And for that, we've basically proposed to apply a second step to this prediction, which is explainable AI. And explainable AI is a wide field with many different formulations, but one of them is formulated as a problem of attribution, where you have a prediction and you would like to be able to identify which features contribute to the prediction. So here you have your input, you have the output of your model, which reconstructs certain proteins. And here you ask for one given predicted protein value, what are the input features that have contributed? And if you now record the path which goes from the output to the input, then you are able to draw basically this pairwise connections between proteins. So if also one advantage compared to correlation is that you don't need to do that at the dataset wide level. You can do that on every data point. So for every subject, for example, for every instance, you get like one of these predictions, and you can basically apply this framework to retrieve the graph connecting these different proteins. And now what you have essentially is a set of networks where for every instance, for every subject, for every set of measurements, you have one such network. So it's a bit overwhelming as an analysis because you have so many graphs, but in practice, you can try to summarize that by performing some clustering. And what we've observed, for example, is that these regulatory networks that we have inferred through our technique tend to cluster across different organ types. So there seems to be organ specificity in the regulatory networks. And this is the kind of resolution of analysis where we intend our analysis to be useful for. But we also wanted to check whether the inferred graph were predictive. And for that, we didn't have ground truth at the organ level, but we had ground truth at the global level. There's a knowledge base called Reactome. And what we did one further step of pooling. So basically a full aggregation of the data to get a single regulatory network. And we could basically compare the inferences of a method compared to the interaction networks, the ground truth interaction networks that are described, for example, in the Reactome database. And we tried, for example, to take the 100 strongest median interactions out of the more than 10,000 ones that were possible. And 56 of them were described in the Reactome database. And we try to compare this approach with some other state-of-the-art method like Genie3, and found that basically in that case, from the highest 100 predictions, only 42 were recovered. So our method seems to perform superior to the existing methods for inferring these regulatory networks. So. Okay, so now a totally different topic, as I was mentioning before. Another use case of explainable AI on unsupervised data, which is here in the context of medical foundation models. And foundation models are basically gaining a lot of popularity due to the fact that they can operate on large amounts of unsupervised data. And they typically work using a variant of contrastive learning, where you are asking, basically, you are generating some surrogate task consisting of determining whether two images given as input are the same or not. And specifically, two transformation of the same image being the same or not. So here we have, for example, a dog. You crop the dog to only include some face or legs. You also do some color transformation, and then you ask whether these things are similar or not. And you basically define the objective as a retrieving or attracting or basically pulling together representations of the different views of the same image and repelling views of two different images. So there are many different methods that are based on this principle, and they have been instantiated in the context of pathology for learning representation of histopathological images. And these things can be, if you have enough data, they can be trained from scratch. So just a large amount of histopathological images. But there is also another competing approach, which consists to derive foundation models from more generalist foundation models. And this is an example with the PubMed clip model, which is applied to radiology data, which derives from the more general OpenAI clip model, which is a general model for images, which is based on defining a matching task between text and images. And so what we wanted to do is to get a bit of insight into the way some of these foundation models in the medical context process data, or if there are some pitfalls with the processing of the data. And so basically these models apply to raw data, so without labels. So we cannot use just standard explainable AI, which will let us attribute a certain classification to the input features. Here, what we have really as input is a representation of the type, either the data itself or some transformation of it. So to try to see what makes it conceptually different from standard explainable AI for classification, we try to study very simple case. So we say, okay, well, let's just imagine that X is the representation of the data. So just the data is the pixels, for example. And we ask, okay, now we are making a dot product between two images, and we are trying to understand what make these two images, X and X prime, similar. Now, this dot product, we can write it as a sum over all the input dimensions. And then basically you see that this decomposes as this sum xi prime. So basically the product of the individual features of the two images. And from there, it's very easy to identify an explanation, which is basically this term, this product is the contribution of feature I to the whole similarity score. Then we try something slightly more complex, saying that the representation is not the data itself, but just a linear transformation of it. And this is represented by the matrix W here. And if you want to rewrite this similarity score, this dot product as a sum, then you cannot get a single sum, you get a double sum over pairs of features from the two modalities. And so if you want to get an understanding of similarity in terms of these pairs of features, in terms of this input features, fundamentally you have to look at pairs of input features. And so this is for linear model. And of course, we wanted to tackle more general representations. So we developed an algorithm called BiLRP, bilinear LRP, which basically allows to generate this kind of pairwise explanations for arbitrary neural network feature maps. And so the way it works is that we pass as input our two images. We are feeding them into the neural network, and then at this level, phi L, it's a representation, for example, the output of clip, let's say. And you can look at the similarity, but by computing the dot product. And then how BiLRP works is basically to apply a LRP backward pass through each of the dimensions, each of the outputs of for the two images, and then compute not a simple matrix product, but a product between the LRP explanations. And as a result, you get an explanation of size, number of pixels times number of pixels, which you can highlight as which you can display as a bipartite graph between the two images. So here you will have basically pixel to pixel matching, and here you highlight those that match the most. So basically, what pairs of pixel or what pairs of patches in the image contributes the most to the similarity. So this is for the method, and now we try to apply this method to our specific task, which is to infer, to understand how specific foundation models for radiology build their representation. And we try one such model, which is the PubMed clip model, which is built on OpenAI clip. And we found something which was not exactly what we expected, which is that there are basically some connections that are made not between part of the chest, which would correspond to specific pathology or to the to what kind of disease is present there. But it looks actually at textual annotations. So it was a bit surprising, and we wanted to understand what is the cause of it, if this really arises in the during the training of PubMed clip, or if it is already latent in the model on which it builds. And so for that, we try to analyze a different model, and in particular clip. So clip is this row, which is basically the model which is used for as a starting point for training PubMed clip. And what we found is that clip employs a very similar strategy. And so clip is general, it's applicable to any images, especially natural images. And we ask, for example, these two garbage trucks, they are predicted to be similar by clip. What is the reason for that? It is not because of the truck feature so much, but because of some copyright tag or some logo which you have at the bottom left corner of these two images. So here, basically, what we can find is that clip tends to rely dominantly on text if text is present in the image, and this reliance on text is inherited basically by the specialized medical foundation model. We also try to investigate other strategies. For example, these two images of people holding a fish do not have text, but even though what is related here are the two fish being of the same type, coho, what the clip model looks at is not at the fish, but at the face of the people holding them, which in some cases might again not be the intended strategy. Also try to look at different models, and we see that basically each foundation models tends to properly model similarity, but based on different reasons. And for example, SimClear, which is another type of unsupervised training algorithm, tend to focus on features that are more semantic, but more focused on the center of the image compared to clip. So we wanted to also try to understand practically what are the possible consequences of such flowed strategies. And so we simulated a downstream task, which is that of predicting COVID versus non-COVID. And we assume that we are basically several months or weeks into the epidemic, and we would like to basically solve this task quickly. And so typical strategy would be to aggregate the few data which have both classes with a more established data sets, which contains basically a bunch of non-COVID cases. And so these two data sets are referred as NIH and GitHub. This is where they are hosted, basically. And we wanted to understand in terms of strategy what the model, how the model would actually perform this detection task. And what we found is that if you just look at the accuracy of the model on the original data, you will find that the accuracy is fairly okay, 87%. But if you specifically focus on the GitHub subset, which contains basically these new cases that have been aggregated from many different sources, then the accuracy drop quite significantly. And what is especially striking is the false positive rate, which here goes from 18% on the original data, so basically mixed data, to 51% on the GitHub data. And basically this basically tells us that the strategy of the model was in fact to look at specific signatures in the more heterogeneous GitHub data sets compared to the NIH, which is a bit more regular, rather than to actually perform the actual intended task. So here we have to be basically careful when working with these medical foundation models, is that there is some kind of domino effect where flows of the more generalist foundation model might propagate into the specialized foundation model, which might then propagate to the actual downstream task. So I just want to summarize briefly what I talked about in my presentation. So why do we care about raw data and we don't go for the classical supervised learning and supervised XAI, explainable AI paths? It's because raw data is very often what is at our disposal. It is available in abundance. And also, if we think about scientific exploration, we don't want so much to put our own labels a priori, because then we are steering too much the process of exploration, and we end up confirming the hypothesis we have built in the first place. So this is the reason why raw data is interesting on its own, and also more generally because raw data is also the way modern machine learning architectures based on foundation models tend to work with. And because they are being used, we also need to extend explainable AI to this setting to make sure that these models are predicting as we intend them to predict. So now, if you basically combine unsupervised machine learning and explainable AI, this can help to enable the exploration of data sources. For example, this tabular data, which we use for trying to infer regulatory networks, and in some cases gain some new insight into what things are related in these networks. And finally, in the second use case, I was talking about foundation models, and what could be identified from analysis is that there is systematic amplification suppression effects that seems to occur in these foundation models. And they might go undetected, right? So they might be solved, but if the model is right for the wrong reasons, then it's not a priori clear why we should worry about that. But if we use explainable AI, you can basically detect these flows, which might not affect the current prediction, but which might affect the way the model generalizes to new data. And here on the right-hand side, you have a list of references to the papers that were covered in this presentation. Yeah, then thank you for your attention.
Thank you for interesting presentation. Since we don't have another panelist from Berlin, if anyone has any question or any topic that you would like to raise based on the presentation from Professor Montavon or from Professor Marcelloni, who presented the hub, please, now we have few minutes for discussion.
We can open also the discussion, the panelists. Okay, just I would like just to thank Gregoire for the presentation. I would like just to open a really short discussion about the explainability on AI, because your topics, of course, was explainable AI in some specific field as medicine or global health in general. And I would like to ask you, just concerning your experience in the use of explainable AI in this subject. And okay, we have a lot of methods now just to make a really explainable AI. But really, it's not clear if we are able just to really make explainable to all the stakeholders. So in your field, just really to introduce the subject, I would like to discuss a little with you. And when you just propose these techniques for explainability, what is the reaction from the specialist in medicine? So they accept, they can really understand very easy this type of explanation. I would like just to have really some feedback from your side.
Yeah, so thank you for your question. Yeah, so regarding what we expect from an explanation, how it should be designed. So this is very important point that you're making, is that it's not only about building new methods, but it's also about being able to evaluate them and to understand what we expect from explanations. And so there is quite a lot of work, which is actually, and some of them are not so novel. Some of them are already from the 90s in the context of expert systems, where people thought also about explanations, and they were asking what are the desiderata of an explanation. And they already thought about it and tried to formalize that the explanation should have fidelity, so it should basically be able to make true statements about what the model does, and not just look nice, because this is always very tempting to have a nice explanation and say, okay, I'm happy with it, but it should really be descriptive of what the model does, in the sense that if the model is doing something wrong, then the explanation should highlight this wrongdoing of the model. That's one aspect. Also, understandability is important. And as you mentioned before, there are different types of stakeholders, and some of stakeholders might understand, for example, different types of features. So for maybe lay people, understanding a target, which might be, for example, health, might be best in terms of lifestyle actions. Whereas for the medical experts, the medical expert would probably look much deeper into the clinical measurements and also potentially what relates to more advanced modalities like imaging, medical imaging, or image or medical sequencing. So yeah, in terms of feedback that we received, so for the first part of my presentation, I was talking about this inference of regulatory networks. So this was actually a collaboration with biologists. So they were actually the one interested in this in the study, and so from that perspective, it's fair to say that they basically gained some understanding and some new insight into this system that they were interested in the first place. In terms of now whether we can gain understanding from foundation models, which is the second part of my talk, then this is also something which is valuable, I would say, to medical experts to know whether the model relies on artifacts, because then it tells them clearly that this is not applicable as it is in a deployment, like it's not applicable or not ready to be deployed, and things have to be changed. Now, when it comes to the more positive outcome, where the model seems to highlight the right features, then yes, then this is one good signal, right? But this is not everything. So there are many different questions that need to be asked before we can really trust the model, and also regarding its applicability in the real world setting. And I'm sure Alexander Meyer, who is not there today, could tell much more about that.
Thank you. Thank you very much.
Any other comment? Please, Stefan.
Thank you. Well, since we have time, and since this is an early event in this new knowledge hub in the Circle U Alliance, you're at the University Hospital, right?
Yeah, that's right.
And I was wondering, I'm in the computer science department in Oslo, and so I was wondering what are the collaborative structures. I mean, you're doing, from my point of view, deep learning method development applied to medical data, but there's a lot of computer science in that.
Yes.
Data science. So how do you work with the other parts of the university that have sort of disciplinary focus on the methods?
Yeah, so we always work in teams that contain specialists on both sides. So it's a no-go for us to write a medical paper just with computer scientists, because then all the interpretation is missing. So this is the starting point, is that if we want to cross boundaries, so trying to apply our method to medicine or to other domain, we first need to think of who to collaborate with. And so we tend to have such collaborations. I'm not sure if this answers your question.
It's a very open-ended question, right? But so I'm guessing you may have doctoral students in your group who actually pursue a doctoral degree in computer science. Is that the case, rather than in medicine?
Yes. So we have so within so now I'm at Charité, right? But originally I was at TU Berlin, also as part of Bifold, and so there are a lot of students that are coming with a computer science background, and when we establish collaborations with medical experts, then these students spend quite a lot of time trying to gain the knowledge in the other field, not all of it, but to it's a good opportunity for people to become fluent in both fields, especially if the collaboration starts really at the beginning of a PhD. Then if the PhD follows that topic for the whole 3 or 4 years, then this is very valuable, because then people become really interdisciplinary.
Yeah, Francesco, please.
Yeah, just a general comment. This, of course, is one of the aim of the Knowledge Hub, just to have this interaction in the multidisciplinary way. And we strongly believe that, of course, the application of AI today have to take in consideration several aspects. We talked about the interaction with medical applications, but of course, when we apply an AI system today, we have to take in consideration also ethics or societal really problems that we can have in the application of the AI system. This is the reason why we started with the Act last year at the level of Europe, but we don't know exactly what's actually this imply in the future, because the application of the Act will start really at the end of this year, at the beginnings of the next year. But I want just to ask to Gregoire another point that is very important for the people working in machine learning. So the availability of data. Most of the applications that we have in medicine or in general, when we really talk about the health, of course, consider a very sensible data. And it's not easy just to exchange, for instance, data from one hospital to another hospital. And especially inside this alliance, this could be very interesting just to really have the possibility to exchange not only just a possible idea about algorithms, but also to have this possibility to exchange data. There are some approaches today, just in some way to work along this direction. I would like to have really some feedback from your side about this type of problem.
Yeah, so I mean, here I cannot say so much about it because I'm not expert on the data acquisition side. But I can say definitely it's a problem that you cannot just share data for obvious reasons across different hospitals. That there are some technical workarounds, so try to anonymize, but this is not also a problem on its own because there's always a degree of anonymization. Cannot and sometimes just by precaution, then there's no disclosure of data at all, which is also a fair point because we never know what kind of capabilities models have at overcoming this anonymization precautions. So yeah, I mean, there are approaches where you can work on try to send the models, for example, share the models, not the data. But here, even that is also not completely proof as a solution because the models might incorporate also some data. So in the very simple context of a support vector machine, which is a classical model of explainable of machine learning, then you have actually some data points which are actually part of the model. So you have a bit less this problem in neural networks, but still there is no proof that things cannot be recovered from this neural network. So ultimately, there has to be some agreement and data sharing agreements that ensure confidentiality on both sides. And this is actually very hard to establish at the level of a single collaboration because it's a big overhead. So it would be very good if there are more like large-scale projects that try to address this data sharing question, but not at the level of a single collaboration, but that can be reused by other collaborations.
Okay, thanks.
Yeah, and one of colleagues sent a link towards something similar that you were talking about. So any additional question or comment or so maybe we could go for a short break a few minutes before and maybe start at 11:30 since University of Oslo has 5 speakers, if I'm not wrong. So maybe it's going to take, we can prolong a bit that part if that's okay with you. Any comment to my proposal?
That means starting the next session 15 minutes earlier than planned?
Yeah, if that's okay with you, because in that sense you'll have enough time since you're a bit crowded in the part regarding Oslo. If that's okay with you, if not, like we can.
I'm just not sure the contributors to that session or people who, according to the schedule, wanted to sort of log in.
Yeah, it's
maybe how about 5 minutes earlier?
5 minutes is okay. So then we have 25 minutes to grab a coffee, do a few push-ups, or take some water, and see you in 20-25 minutes, if that's okay with you.
Thank you.
Okay. Once again, Professor Montavon, thank you for your presentation, and see you soon.
Yeah, thank you. Thank you for inviting me.